You know how your computer can instantly rotate a photo? Or how data scientists somehow make sense of these huge, massive data sets? Well, it turns out that behind a ton of our modern tech, there's this really powerful mathematical tool that's basically just a simple grid. Today, we're pulling back the curtain on the matrix. So let's start with a puzzle. How do we give a computer a precise command like rotate this image exactly 90 degrees or stretch it to be twice as wide? The answer is surprisingly elegant, and yeah, it all comes down to the matrix. And it is everywhere. I mean, we're not just talking about computer graphics. Matrices are the absolute backbone for solving complex systems of equations. They're totally essential in modern physics, they're the heart of data science, and they pop up all over the place in programming. It's truly one of the most useful tools in all of mathematics. Okay, so what in the world is a matrix, really? Let's break down this basic building block. And don't worry, we're going to keep this super simple and intuitive. At its very core, a matrix is nothing more than a simple grid or a table of numbers. Seriously. If you've ever used a spreadsheet program like Excel or Google Sheets, you already get the basic idea. That's it. Now, the more formal definition is that a matrix is a rectangular array of numbers, organized into horizontal rows and vertical columns. And we define its size by saying rows by columns. So, for example, a grid that has 2 rows and 2 columns, well, we call that a 2 by 2 matrix. Simple as that. Okay, so now we know what a matrix is. The next logical question is, what can we do with them? Let's learn the simple rules of the game, starting with the really easy stuff. So, the first few rules are super intuitive, pretty much exactly what you'd expect. For 2 matrices to be equal, they have to be the exact same size, and every single number inside has to match up perfectly in the exact same spot. And for adding or subtracting them, same deal. They've got to be the same size, then you just add or subtract the numbers in the matching positions. Top left with top left, bottom right with bottom right, and so on. Easy. Now, scalar multiplication, it sounds kind of fancy, but it's probably the easiest one. It just means you take the whole matrix and multiply it by one single number. We call that a scalar. That one number on the outside just gets multiplied by every single number on the inside. All right, we've breezed through the basics, but now it's time for the main event. This is the move that really unlocks the true power of matrices. Let's dig into matrix multiplication. Before we dive into the steps, here is the one key idea you need to hold on to. To get just a single number in our final answer, we're going to combine one whole row from the first matrix with one whole column from the second one. Just keep that in your head, row times column, row times column. So here's how it plays out. To find that very first number in our new matrix, we start by taking the first row from matrix 1. Then we take the first column from matrix 2. We multiply their matching entries together, first with first, second with second, and then we add those results up. That sum, that's the very first number in our new matrix. And you just repeat that same exact row times column dance for every possible combination to fill out the whole thing. Now, this brings us to the single most important and maybe the weirdest rule in the entire world of matrix math. Order matters. A lot. You know, with regular numbers, 3 times 5 is the same as 5 times 3. No big deal. But with matrices, multiplying A times B is almost never the same as multiplying B times A. This is a huge difference, and it's absolutely crucial to remember. Okay, we've learned the rules, we've done the work, now it's time for the payoff. How does this simple grid of numbers actually do stuff in the real world? Let's finally connect all these operations back to computer graphics and solving equations. Check this out. This really shows how elegant matrices can be. Over on the left, you've got a standard system of equations, and on the right, it's the exact same information, just neatly organized into matrix form. See how we've pulled out the coefficients, the variables, and the answers into their own little boxes? This isn't just about looking tidy. It actually unlocks incredibly powerful and fast ways to solve for x and y. And here it is, the answer to that question we asked at the very beginning. How do you tell a computer to manipulate an image? You use something called a transformation matrix. There are literally specific matrices for everything. One matrix for rotating, another for reflecting, another for stretching or scaling. And you know what's really cool? If you want to do 2 things, like rotate an image and then scale it up, you just multiply the rotation matrix and the scale matrix together. You get one new super matrix that does both jobs at once. All those amazing visual effects, they're just clever matrix multiplication. Okay, so let's do a super quick summary.
Just like with regular numbers, matrix addition is commutative. A plus B is the same as B plus A. The distributive property also works just fine. But that big one, the one that really sets matrices apart, the idea that A times B equals B times A, that is a definite no. That's the key thing to take away.
All right, so you think you've got the hang of this. Let's try a little challenge. Using that row times column rule we just learned, can you figure out what x is here? Just take that first row, 1, 2, multiply it by the column, x, 1, and you know it has to equal 5. Go ahead and pause the explainer here and give it a shot. So we started with what just looks like a simple grid of numbers, and we ended up with this incredible tool that can solve complicated equations and create amazing computer graphics. We've basically learned the fundamental language of matrices. So the real final question is for you. Now that you know this language, what hidden patterns out there would you want to organize, and what kinds of problems would you want to solve?
Welcome. In this explainer, we're going to break down the powerful and, surprisingly intuitive concept of vectors. They are a fundamental tool, not just in math, but in physics, computer graphics, and a whole lot more. So, to kick things off, let's think about something you've probably seen a million times. When you move a character in a video game, how does the game know exactly where to send them? What information does it actually need to pull that off? Well, it turns out the answer boils down to just two super simple questions. That's it, just two. First, you gotta know, how far does the character need to go? And second, which direction should they head in? If you know both of those things, the distance and the path, you know everything you need to describe that motion perfectly. All right, so what we've just been talking about, that's the core idea. Now let's give it its official name. That combination of distance and direction, well, that's a vector. So here it is, the official definition. A vector is basically an arrow. Its length, which we call magnitude, tells you how far, and the way it's pointing tells you which direction. Simple as that, right? Okay, now this next part is really, really important. A vector's identity comes only from its length and its direction. Where it starts, that doesn't matter at all. So an arrow that shows a 5-mile trip northeast in London is literally the exact same vector as one for a 5-mile trip northeast in Tokyo. They're considered equal. All right, so we get the whole arrow thing right. It's a great visual. But to really make these things work for us, we need a way to talk about them with numbers and symbols. We got to learn their language. And basically, there are too many ways we can do this. We can describe it geometrically, like an arrow that goes from some point A to another point B, or we can use coordinates, which is just a pair of numbers describing the movement, how much it moves left or right, and how much it moves up or down. And this is the key thing to get your head around. A vector's coordinates, they're not a spot on a map. They are the journey itself. To find them, you just subtract the starting coordinates from the ending coordinates. Honestly, this is the best little shortcut you can remember. Anytime you need to figure out a vector's components between 2 points, just think final minus initial. That's it. It'll save you a ton of headaches. Okay, this is where vectors get really fun. I like to think of them as Legos. They're not just static arrows. We can snap them together, take them apart, and stretch them to build way more complex ideas. So visually, the way we add them is called the head-to-tail rule, and it's super intuitive. Imagine you're taking 2 separate trips. First, you follow vector A. Then, right where you finish, at the head of A, you start your next trip along vector B. The new vector that takes you directly from your original starting point all the way to your final destination, that's the result. That's A plus B. And you know what? Doing it with numbers is even easier. Seriously, you just add the x parts together and then you add the y parts together. Done. So what about subtracting? Well, it's just a clever little trick, really. Instead of trying to subtract vector B, what we actually do is we add negative b. And what's negative b? It's just the b vector but flipped around 180 degrees. Once you flip it, you just add them together using that same head-to-tail rule. We can also stretch them, shrink them, and even flip them around. We do that by multiplying the vector by a regular old number, which has a fancy name, a scalar. So multiply by 2, and the vector gets twice as long. Multiply by -1, and it just flips its direction completely. So, why are we doing all this? Adding, scaling, what's the point? Well, this is where we get to solve actual problems, often in a way that's much, much simpler than you'd expect.
Take finding the midpoint of a line, for example. You might remember some clunky formula for this from geometry class. Well, vectors give us an incredibly clean, almost elegant way to do the exact same thing.
And check out how simple this is. You take the vector that points from the origin to point A, and you add it to the vector that points from the origin to point B. Then you just divide the whole thing by 2. You're literally just averaging the 2 positions. It's so clean.
Okay, let's zoom out for a second as we start to wrap this up. What is the big advantage of thinking this way? What new power does this give us? This, right here, is the real magic of vectors. They're like a translator. They let us take a messy geometry problem with all its shapes and angles and lines and turn it into clean, simple algebra that we can just solve. Now, as you start playing around with vectors yourself, here are a few common pitfalls to watch out for. First, always remember a vector is a journey, not a destination. Second, when you subtract, just think add the opposite. And finally, don't forget that a vector is a package deal. You need both its length and its direction.
So, that's a quick tour of what vectors are all about. The real takeaway is to start seeing them everywhere. The push of the wind, the path of a baseball, your walk to the corner store. They can all be described with a simple arrow telling us how far and which way. So, what's the first thing you're going to describe with an arrow?